Welcome to all you grade 10 math learners. Grade 10s, it is a Monday and it's Maths Monday here on Learn Extra Live. I am Looney and with me is Tamlin. How are you doing, Tamlin?
Very well. How are you?
I'm great, thanks. So
Good.
what are we doing on today's show?
Today we're doing a very important section,
Yes.
one which definitely follows its way through from grade 10 all the way to grade 12,
Right.
and it's functions. So for those out there who are, even if you're in grade 11 or 12, if you're wanting to just revise the basics again, go back to grade 10 basics, watch.
Okay, so you heard it, guys. Tamlin, I'll send you to your board.
Thank you so much.
Guys, don't you forget to contact us on the show throughout the whole show. I'll be on Facebook. Our Facebook page is facebook.com/learnextra. On Twitter, I am on @learnextra. And don't forget to download all your show notes, your schedules, and the videos at learnextra.co.za/live. It is a Monday. It's maths, so grade 10s. I hope you're ready. Let's take the show away. Tamlin?
Thank you so much. Right, welcome Mindsetters, and I hope you are ready to learn a lot about functions today. Okay, today we're actually specifically looking at two types of functions. We're looking at linear and hyperbolic functions. And we're going to take a really close look at what is a function, how does it work, what do we do with it, and hopefully at the end of it you'll have a really good grasp on what it is that we are doing with functions. Okay, so let's have a quick overview as to what we are going to be doing in our lesson today. The first thing we're going to have a look at, guys, is what is a function and a relation. Okay, we're actually going to just define it for you, talk about what they are. All right, once we've done that, we're going to teach you a little trick. It's called the vertical line test. And this vertical line test is a little trick we use to help us determine if something is a function or not. Okay. Then we learn about the mapping and functional notation. This is important because it's just a type, it's a way of writing. When we're referring to a function, it's the way we refer to a function in our mathematical language. And then we're going to be having a look at sketching. Okay, this is important, guys. Sketching and determining the equation of a linear function. And once we've had a look at that, we're going to learn to sketch and to determine the equation of a hyperbola or a hyperbolic function. All right, so we've got lots of work to do. Hope you guys have got your pens, calculators, and papers ready. Let's have a look at all of this. Okay, key concepts. Let's talk about a relation, all right? Essentially, a relation, all right, is a rule in which each element of the one set of numbers is related to a number in another to another number in another set of values, okay? And we do it according to a specific rule. All right, let me make more sense of that. We have a whole lot of values, x values, and we have a rule. We're going to call it an algebraic rule, okay? So essentially something like y equals 2x plus 3, okay? That's our rule, all right? Now, if we took a whole lot of x values, which we're going to learn are independent values or variables, and we substitute them into the equation, okay? I'm sure a whole lot of you, or I'm sure you remember from earlier years, our machine diagram. As we feed our variables into the machine, into our rule, so out comes the other values, which we're going to call our dependent variables, and those are our y values, okay? So the relation, the rule in which that we're using is going to determine the type of number that comes out when we feed in a value for x, okay? So it's like a machine diagram as such. When we talk about a function is a special type of relation, okay? Now, basically, this is what we've got. A function is where every value for x will only ever be related to one value for y, all right? You will never have a value for x related to two values for y if it is a function. So that's what a function is. It's a special type of relation, and that is where its one x value is only ever connected to one y value, all right? Okay. The notations that we briefly mentioned just now, we've got our mapping notation. Okay, the mapping notation, just for now, you can take note of, looks like this. I'm going to discuss it in a bit more detail in a minute. And your functional notation, if you can take a look, just take a note of it, looks like that. It's this f bracket x, which is equal to your rule, your 2x. Okay, so for now, just take a look at it. We'll deal with it now in more detail. And again, we will deal with this in more detail, but if I've got a linear function, all right, a linear function has a special, unique standard equation, all right? And its standard equation is y equals ax plus q. That's the defining equation of a linear function. And a hyperbola has got has got an equation of y equals a over x plus q. And those two equations, if you have got an equation in the form of ax plus q or a over x plus q, it will either give you a graph that is linear or it's going to give you a graph that is a hyperbola. Okay. All right, so a function we've established is a relation in which every x value is only ever related to one y value. All right? Relations are where we've got a whole lot of values for x and we stick it into a formula and we work it out inside that formula, and out comes the value for y, giving us our independent x variables and our dependent y variables together, which make coordinate points, which we actually plot when we're actually sketching our functions. Okay. All right, so we've had a look at most of this. Let's just have a quick look over here. So as an example, if I've got a relation is any rule by means of which an element of the first set is associated with at least one element of the second set, we've got an example over here. So let's take, for example, we've got a set of x values giving us -2, -1, 0, 1 and 2, okay? And we've got this rule, this little relational rule there, which is telling us that y is equal to 3x. Okay, so the idea here, guys, is that each one of these x values gets substituted into the equation of y is equal to 3x. So let me do the first one with you. If I take the x value of -2 and I substitute that into my x, we land up with a value of -6, that being the y value. Okay, and together this little pair will then will ultimately form a coordinate point. Okay, and a coordinate pair is what we plot on our Cartesian plane. Okay, different ways of representing a relation, just so we are aware of it. We can do it by means of a table, just as I've illustrated to you above. All right. We can show relations in terms of ordered pairs. Okay, ordered pairs would then be saying, instead of having it in this way, I would have a bracket and I would show that it's -2 and 6, like, -6, like so. We can show it in set builder notation, or we can show it on the Cartesian plane where we actually plot the point of -2 and -6. Okay, that's a very rough drawing, but that's sort of what it would look like on your graph. Okay, so those are different ways that we would represent your relations. All right. Then we talk about two different concepts which we hear quite often when we're dealing with functions and relations. And just to make sure that you guys understand these, we talk about domain and we talk about range. Now, for those of you who have done functions at school, I'm quite sure you've heard this plenty in class. Domain and range, okay? Basically, domain is all the x values that we span across in our set of numbers. So everything from the lowest x value up to the highest x value, that would represent your domain, all right? The range is everything on your y-axis. So your lowest y values up to your highest y values is then your range. So domain, the x values that your function is covering, the range, the y values that your function is covering, okay? And just to show you how we would represent it if I was looking at it on the Cartesian plane, if I had a graph going from -2 to +2, that's on my x-axis, that would then show me this over here. So I would say that the domain is x as an element from, okay, take note that I've used square brackets over here and over here, grade 10s, to indicate that I'm including -2 as my lowest x value, all the way up to +2, which is my highest x value, and we're including both of those values. All right, so that's the domain. Now let's have a look at what the range would be. Now the range, don't forget, is the y values. What was the lowest y value? Up to your highest y value, which means we're looking at it in this direction here, up to there. So our lowest y value is -6, and our highest is +6. And again, I'm using square brackets to indicate that they are being included. So they're included, and that's how we show square brackets. If it was not included, just to give you an idea, if it was not included, you would quite clearly see an open dot on your line. And just remember that, I'm quite sure we've covered this in your set builder notation at the beginning of the year. Open dots are going to represent a value that is not actually included. And as far as interval notation goes, we use round brackets to indicate those. Okay, right, guys. Now let's have a look at some examples. So we know that a relation is where every x value has only one, sorry, a function is where every x value has only one y value. Right, here's my trick, okay. Often a question is going to come along where they give you a picture and the question will be determine if this is a function or not, okay. Now we know that a function has got to be where every x value is linked to only one y value, all right. And a useful little trick to do this is what we call the vertical line test, and this is what the vertical line test looks like.
Tamlin,
Yes.
before we start the question, can we go for a quick break?
Oh wow, that was very quick.
Guys, we are going to take a very short break, but don't go anywhere. It is Earth Day, so I hope you're taking care of the earth. You're not littering, you're recycling, you're doing things good, you know, you're enjoying this mother planet of ours, and I hope you guys are enjoying the show. We have lots more coming up, so don't you go anywhere. We'll be back right after the break. Welcome back, guys. If you've just joined us, it is grade 10 maths on a Monday. I am Looney, and joining us in studio is Tamlin. We're doing functions for the grade 10, so I hope you guys are listening and you guys are writing down everything that you need to write down. I'd like to remind you guys about the Future Stars competition that's going on. You can go into our page, we have all the information there. Enter your friends, enter yourselves, ask your friends to vote for you on the Future Stars competition page. And if you need any information, we've got everything on our page. Guys, don't forget to ask me any questions that you may have about the lesson on Twitter and on Facebook at LearnExtra and on facebook.com/LearnExtra. Tamlin, take it away.
Thank you so much. Right, so we've said that relations are a whole lot of x values that are connected to a whole lot of y values according to a specific algebraic rule, okay? If that rule is a linear equation, when we take the x values and y values and we plot them, they're going to make a straight line graph. If the algebraic rule is a hyperbolic rule, it's going to make a hyperbola. All right. Then we said specifically that a function is a special type of relation where the values for x are only ever connected to one value for y. Okay. Now, before the break, we were talking about a vertical line test, and it's just a test to determine if a diagram that's been given to us is a function or not. All right. So let's have a look and see this vertical line test over here. Right, if you're being asked to identify if it's a function, what you need to do is take your ruler and you need to hold it vertically across your graph like I've got over here, all right? And you're going to move your ruler horizontally from left to right along your x-axis like so, all right? And the idea is this, so we go from the lowest x values up to the highest x values. And as we run our ruler across, can you quite clearly see that we are only ever cutting one value for x as the one value for x is only ever connected to one value for y. So basically the ruler is never crossing the graph more than once. And that's the key to your vertical line test, is that as you drag your ruler across the graph, it must only cross the graph once. If that happens, we know that it's a function. So if with regards to this one, is it a function? Yes, it's a function because I know that my ruler only crossed my graph only ever once. Let's apply our vertical line test to this semicircle. As I go across, I can see that this ruler is only ever crossing the graph once at any given point. So is this a function or is it a function or just a relation? It's a function, okay? Let's look at a graph like this, okay? If I take my ruler from left to right and I run it across, let's see, does it cross the graph ever more than once? Okay, it's only crossing the graph at one point, and all the way across you can see that it's never actually crossing it more than once. So once again, this over here would represent a function. All right, we've got one more to try. Let's take our ruler and let's go across. Okay, vertical line test. Drag it across now, guys. Let's watch here. Can you see that at this point, if I draw a line through it, the graph is crossing over there and it's crossing over there, which means that it's passing, the ruler is passing through a graph at 2 points. And because it's passing through 2 points, it means that that particular x value was actually related to 2 y values, meaning that it is not a function. So in that case, your answer would be not a function. All right. So that's how you apply your vertical line test if you are asked to identify if a diagram is a function or not. Okay. Okie dokes. Let's see now what our notation is all about. Okay. What we've said over here is that because functions are special relations, we give them special notations. We refer to them in special ways, okay? And essentially, the one way is your mapping notation, and the other is your functional notation, all right? Now remember, the concept of a functional relation is that we've got x values, which we subbed into an equation, and out came y values, okay? So your y values are very dependent on what went into your equation as x values. I'm sure you guys all agree with that. It depends on what went in as an x that came out as a y. So, what we say over here, mapping notation. Let's just have a look over here. This is our mapping notation, and this is what it looks like, guys. We've got f semicolon x is mapped onto, and we show that just by a little arrow, to 2x. So, as you can see what it says here, this reads f maps x onto 2x, all right? So, if x is equal to 3, is an element of the domain. Remember, your x values are your domain, all right? Then the element of the range, remember the range is the y values that came out, is going to be 2 times 3. Remember that obviously the 3 had to get substituted into the x. And obviously what we get there is 6. So we say that 6 is the image of 3 in the mapping of that relation. Okay, so putting a long story short, when we put 3 into that equation, what came out as the dependent y value that's part of the range, is then 6. Okay, so that's your mapping notation. It's just a way of showing functions. Okay. And your functional notation, another way, a very common way, guys, of showing showing functions. Okay, probably slightly more common than your mapping notation, is your functional notation. All right, functional notation is going to look like this. We say f of x, and we show it inside a bracket, and we read it f of x is equal to 3x. Okay, sorry, that should actually be 3x over there then. So f of x is equal to 3x. All right, so that means that f of x represents the value that's going to come out when I substitute an x value into my equation. All right? So something that you must be quite clear on is that you understand that, in fact, this f of x over here is really talking about the y value that comes out when we substitute an x value in. Okay, so f of x means the value for y that came out according to whatever x value went into the equation. I hope that makes sense to you guys. Okay, Looney, does that make sense to you?
Of course.
Okay, right, let's have a look then and see what we've got in terms of this notation over here. Just to get you guys familiar with it, let's take an example. We've said that f of x, okay, now remember that's just another way of saying y. We're talking about y there when I refer to f of x, okay? F of x is equal to 2x squared minus x plus 1. All right, so this is what they're asking us to do. They said determine f of 2. All right, so let's think about this for a second. F of 2 means I want to know what is the y value when my x value is 2. All right? So in order to do that, what I'm going to have to do is take my equation, and everywhere where we've got an x, we are going to have to substitute it with what we've got inside this bracket over here, which is 2. All right. So once we've done that, we'll then actually just work it out. So that's going to be 4 times 2, which is 8. I've got minus 2, and I've got plus 1. And that's going to give us 7. Okay. So therefore, according to this function, according to this relational rule over there, when I've got an x value of 6, and I plugged it into the equation, out came a y value of 7. Okay, and if we took a whole lot of values for x and we substituted it into that particular equation, because that's a special type of equation, it's always going to give us back a particular type of graph, okay? As would it do if I had a linear equation or a hyperbola equation, okay? All right, so just to make it a little bit more algebraic, what if I was saying f of a? All right, so again, what that's saying is that in terms of a, what would the y value be if my x value was a? Now, they can do this to you, okay? It doesn't have to be numbers. I'm sure by now you know in maths, we love to throw letters in there. It doesn't have to be numbers. So in terms of a, which is saying your answer is going to have a in it, but what would the y value be if the x value was a? All right? Exactly the same process happens. We substitute a into every place where you had an x, and out comes the y value. So we're now substituting a in there and a in there, which gives us, I'm just going to have to write it on the side here because of space, it's going to give me 2a squared minus a plus 1. Now, it doesn't look very neat and tidy, I agree with you, but that's the y value that comes out where the x value was a. All right. Right, one more thing to do with notation. What are they asking me for here, grade 10s, if I've got f of x is equal to 4? All right, so what are they asking me for? Remember, the thing to relate to is what is the value, what is f of x? All right, now remember, f of x is actually the y value. All right, so this time we're asking it in reverse. We're saying, well, if the y value was 4, what's the x value that's related to it? Would I do it exactly the same way as I did where I had x's? Absolutely, except this time I'm going to substitute 4 into the place of your f of x. Okay, so our f of x equation was 2x squared minus x plus 1. That was our equation. And we've now said that f of x is actually the value of 4. All right, so if I sub in that in there, do you agree what we've got is an equation which is actually a quadratic equation to solve for x? So we're going to bring my 4 over, and negative 4 plus 1 is going to give us negative 3. Okay, this is just a good old quadratic equation which we need to solve. All right, so we're going to have a 2x and an x. That would have to be 3 there, and that would have to be 1 there, and we'd have to have a minus and a plus. Okay, so x is equal to 3 over 2, and x is equal to negative 1. All right. Grade 10s, I've got a question for you, which I would actually like you to think about while I move on just over the course of the lesson. I want you to establish for me, I've got two values for x here. I've got x, which is equal to 3 over 2, and I've now landed up with x is equal to 1. All right. And the y value was 4. Think about it, and I'd really like you to tell us, is that a function or is it a relation? Okay, now remember, functions, every value for x has one value for y. All right? So look at that example, and I want you to determine, would that be a function, or would it just be not a function, which is then just a relation? Okay, so think about that, and let Looney know, please. Okay. All right, we need to now get a little bit more specific in terms of the type of functions that we have to work with. Okay. The first two types of functions we're looking at today is our linear and our hyperbolic. Okay, so let's have a look at linear, and let's talk a little bit more about it and make sure we understand how this all works. Okay. We have relations, and x values get substituted into a relational algebraic rule, all right, and outcome y values. Now, this is the story. If we have got an algebraic rule that is in the form of ax plus q, if it ever fits into that standard equation, what you are going to have is a linear relationship between the x's and the y's, which means that if we take the x's and the y's and we turn them into coordinate pairs and we plot it, you will always get a straight line graph. Okay, so this over here, this equation determines the type of relationship between the x's and the y's. And the relationship, because of that standard equation, is linear. Okay, so the second you look at an equation, guys, and you can just see that I've got an ax plus q form, you know it's going to be a straight line graph. All right. Okay, so what does the a actually mean in our standard equation? Okay, you can see we've put here that the a represents the gradient or the slope of a straight line, okay? If you were to consider climbing Mount Everest as opposed to just the streets up, just sort of the slope of your streets, let's say, the one is much steeper than the other. So that would be the slope or the gradient of your line, okay? And that A determines the gradient, all right? Now, we've actually been a bit more specific here in saying that if you've got a straight line graph where your A value is greater than naught, so in other words, your A value is positive, you've got a positive gradient. And a straight line with a positive gradient will always be in a climbing direction. Okay, I always say to my class, it's either climbing or it's sliding. So a positive, you're climbing up the hill, okay? And that would be your positive A value. That's determining the direction of your slope. If your A value is negative, so in other words, it's less than naught, then I would be sliding down the hill, and that's giving you your negative gradient, okay? Positive gradient, which is determined by the A of your linear equation, that's your gradient climbs. If your A is negative, your gradient slides down, being a negative A value. Just quickly before we take a break, the Q, all right, the Q very simply represents the y-intercept. And another way we could phrase that is, where does the line cut the y-axis? All right, so in my diagram, we've shown you over here that Q, I've said that Q is greater than naught. So if Q is greater than naught, what we're telling you there is that the y-intercept is positive. It's above 0. And if we look there, can you see that if I show you where I've got my y-intercept, it is a positive y-intercept. However, if I've got a Q value that is less than 0, that's telling me that my graph is going to be crossing the y-intercept on your negative axis, so giving you negative values. So that's what the A and the Q do. All right, I think we're going to have a short break, and when we come back, I'll show you how we're going to plot these.
Guys, we're going to go for a very short break, but don't forget to stay tuned. Don't forget it is Earth Day, so remember to recycle, reduce the use of electricity, water, and all that stuff. Encourage all your friends to stop littering and all of that. I'd like to send a shout out to Calvin, who's watching. He's actually in matric, but he says he's watching just to revise. So I encouraged him because for the finals, they actually bring up so many questions from all the previous grades. Guys, stay tuned. We will be back straight after this break. Welcome back, all your grade 10s. I hope you're refreshed. You got some water, you got some juice, have all your notepads down there. You're writing down everything that Tamlin's teaching you. Just to tell you guys what is happening, Tamlin actually asked a question. She was doing a question and then she asked if you thought it was a function or a relation. And Apiwe and Siri actually got it right. It is a function. Tamlin told us it's a function. So well done to you guys. So Tamlin, take it away.
All right, let me very quickly explain to you why it's a function. Okay, I'm going to show it to you by a method of what we call a Venn diagram. Okay, so a Venn diagram basically looks like this. I've got a circle over here representing the x values, and I've got a circle over there representing the y values. So the one x value we had was 3 over 2, and the other x value we had was -1. And the only y value we had was 4. So we said that this 3 over 2 was connected to that 4 over there, and -1 was connected to the 4 over there. So are each of the x values connected to only one y value? Well, yes, okay, there's 2 x values, and they happen to be connected to the same y value, but it's still a 1 x value connected to one y value, and that's why, yes, it is still a function. Okay, so well done, guys. That was well done. Okay, what we're going to now quickly have a look at is sketching a straight line graph. Okay, there are many different ways in which we can go about drawing a straight line graph. We can either plot a table. All right, you've got values for x, you sub the values for x into your equation, and we get the values for y. All right. There's another method called the dual intercept method, where I work out the x-intercept and I work out the y-intercept and we plot. Or we could even use our calculators. Can you believe it? Okay. So what I'm going to do, guys, is show you each of the methods very quickly so you can decide which of the ones you wish to use. Okay. Right. Table method is going to go something like this. We're going to have ourselves a table where we're going to have a couple of blocks in it. And we've got values for x and values for y. I'd give myself a couple of values to work with. You don't need to go too far, though. It's not necessary. And what we do is we take each value and we sub it into the equation. So the first one would be negative 2 times by x. No, sorry, let me just take that out. It's not negative 2, sorry. Positive 2 is the equation. So positive 2 times by x, which is negative 2 plus 4. Right, so that's giving me negative 4 plus 4, so there I've got 0. If I substitute negative 1 into my values for x, that's giving me negative 2 plus 4, which is giving me positive 2. So that was 0, that was 2. If I substitute 0 into the equation, I'm going to land up with just 4. If we put 1 into the equation, that's going to give me 2 plus 4, which is 6. And finally, if I put 2 into the equation, that's going to give me 8. Okay. All right, so that's fine. It gives me the values that I need, but I'm sure you agree it's a little bit untidy and it requires quite a bit of working out. So I would suggest to you that if you're stuck on it, use your table method. Otherwise, if you're needing to push yourself with time, try not using the table method. Let's see if you can get an understanding of this next method over here. I'm going to do it in a different color. This over here we're going to call the dual intercept method. Okay, dual intercept, basically we are working out the y-intercept and we are going to work out the x-intercept. Remember, that's where the line cuts the x-axis and where it cuts the y-axis. And the way we work out the y-intercept is we say, let x equal 0. And to work out the x-intercept, we say, let y equal 0. So therefore, if I've got my equation, I'm going to say y is equal to 2 times 0 plus 4, which is going to give us just 4. And y, oh no, we're going to make y 0, so let's just take that out. Okay, we want y to be 0, and that's equal to 2x minus plus 4. So therefore, I would land up with negative 2x is equal to 4, so x would be equal to negative 2. Okay, so let's plot this now. Let's draw ourselves an x and a y axis. I'm going to do it over here, and let's plot our points. Okay, we had 1, 2, 3, 4, 5, and in fact we went a bit further on, so I'm just going to go all the way up to 8 over there. Okay, so sorry, I had to miss out 7, but not too serious. Negative 2, negative 3. Right, we've got 1, 2, 3, 4, 5, 6, 7, and 8. And, oh, no, negative 1. Negative 1, 2, 3, and I think we are going to be okay with that. All right, so let's use our table first. Let's plot the points that we had. So the first one I had was negative 2 and 0. So my x is negative 2. My y is 0, which means we are sitting over there. That's my point. The next point we had was negative 1 and 2. So x is negative 1, y is positive 2. That's going to give us that point over there. The next line that we have, next point I have is 0 and 4. So x is 0 and y is 4. That is going to give us this point over here. And I've got 1 and 6, where x is 1, y is 6. X is 1, y is 6. And finally, where x was 2, y was 8. So, can you see that we've landed up with a line that is a straight line? And that's no coincidence, guys. I knew it was going to be a straight line graph. And how did we know that? Because if we go back to our original equation, did it form or did it fall into the standard equation of y equals ax plus q? Yes, it did. The a was 2, the q was 4. Let's test something quickly. Remember we said the a represented your gradient, and if your gradient was positive, it was a climbing graph, right? Let's check ourselves. Is that a climbing gradient? Yes, it is. Okay, so we've got a positive a value, and the q was positive 4. And remember, that was where your line was crossing the y-axis. Now, positive 4, yep, that's exactly where it's crossing your y-axis, so that is your straight line graph. All right, now, just to bring in this point over here, if you didn't use the table method and you used the dual intercept method, you landed up with two values. You had x was equal to -2, and you had y was equal to 4. Now, if you just had those 2 points there, we would plot that y would be equal to 4, and x would be equal to -2, and if I were to draw that line, let's just choose a different color, if I were to draw that line, do you guys agree it would be exactly the same line? So whether you use the table method or whether you use the dual intercept method, you are going to get the same line, okay? So you need to play with it. You need to work with the method that suits you, okay? And that really is the case. One more method is using your calculator, okay? So let's show you how that's going to work. All right. I hope you've got your calculators with you, and just work with me as I'm doing it. Follow the buttons that we're pressing, and this can be used to sketch not just linear, any of your graphs. Okay, so let's have a look here. The way we do it is this. We take mode, we press mode, and then I have to press 3 for table, okay, and we bring up an f of x equals, which now we recognize is our functional notation. Remember, f of x represents the y value that is connected to the x value that we're subbing in, okay. So what was our equation? It was 2x. Now on the calculator, the way we get x is we press alpha, and then we press this button over there. Can we see that that gives us an x? So we had 2x plus 4. All right. So once you've typed your equation in, all right, then what you do is you press equals, all right, and your calculator asks you start. It's asking you, where must I start, okay? It's suggesting that you start at 1, but we're going to suggest you start a little bit further back than that. So let's start at -3, all right? It's just giving us a few values on the negative side, which will give us a bit more space to work with. Once we've said that, we press equals, and the calculator says, where must I end? All right? Well, I started at -3, so let's make it the same on the other side. Let's end at +3, okay? And press equals again. It says, what steps must I go in? Must I go in steps of 1 or 2? Or how must it go? So it's asking, should it go in steps of 1? And you're going to say, yes, we want it in steps of 1. So we just press equals. And what comes up is a table of all your coordinate points. Okay, so I hope you guys can see this on the screen. I know that it sometimes looks a bit small, but if you can't, sit with your calculator and work with it, because you might find this a bit handy, okay? And essentially, this column over here is showing us the x values, and the one next to it is the y value that's connected to it, and each of those form the coordinate points that you're going to plot, okay? So again, go play with that. See if it works for you, because it's also a nice handy way of checking, if nothing else, that your line is correct. Okay, guys? So that is how we sketch a straight line graph. Right, looking at this equation over here, I've got x plus 2y equals 6. My question is that a linear function? How do we know? All right? Now, with a function, the standard equation of a linear function, remember, was y equals ax plus q. So can you guys quite clearly see that y is on its own? Y is isolated on its own on the left-hand side of the equation. Now, the problem with the way we've got it over here is that y is not on its own, and that we don't want it like that. So we need to rearrange our formula, and we need to get it into the standard form of ax plus q. All right? So what does that mean? We need to get y on its own. So that's what I want to get on its own. So the first thing that needs to move is my x. All right? So we are going to say that 2y is equal to -x plus 6. And then to get y completely on its own, we need to divide it by 2. And everything gets divided by 2, meaning I've got negative x over 2 plus, and that will become 3. So, is it a linear function? Well, if we look at it, I've got y equals ax. My a in this equation actually works out to be negative 1/2. And the q in my equation works out to be positive 3. All right? So because my a is negative, is my gradient a climbing gradient or is it a sliding gradient? I'm sure you guys are saying to me, it's sliding. Okay. So it's going to be just roughly, it's going to be a negative gradient. It's going to face that direction over there. What is this telling us? It means that I've got a y-intercept at positive 3. All right. How are we going to plot it? You've got all these different methods that you can choose from. I want you to use the method you are comfortable with. The one that I'm going to use is the dual intercept. I'm going to work out the x-intercept and the y-intercept and plot them. Okay. So we're going to have my x and my y-axis. All right, we should always label them correctly. So I've got my x and my y-axis. Right. If I let's do the working out at the bottom here. If I let x equal 0, remember that's working out your y-intercept. So I would say y is equal to negative 0 over 2 plus 3. And in fact, that gives us something we already knew. We knew the y-intercept was 3. And let y equals 0 means I'm going to land up with 0, which is equal to negative x over 2 plus 3. All right, let's bring our 3 over. So we're going to land up with negative 3 equals negative x over 2. Instead of dividing by 2 on the one side, I'm going to times it by 2 on the other side. So we get negative 6 equals negative x. And if I divide by negative on both sides, we get positive. So I get x is 6 and y is 3. So my x value is going to be a 6 and my y value is going to be a 3. And from there, we can plot our line. Double check this for me, guys. Is this, let's just put it there, is that the negative gradient that we knew it was going to be? And I think we all agree that that's a negative gradient, so we're happy with that. And does the line pass the y-axis at positive 3? Yes, it does. Okay. So my gradient was negative, and my y-intercept was 3. Okay. So that's how we work with a linear function. All right. Very quickly, we're going to have a look, guys, at some hyperbolas, just so we're skipping through a few things over here. In fact, let's not rush it. We'll have a look at some other things quickly here. All right. Before we go into hyperbolas, let's finish off our linears properly. If you have got, I want you to take a careful look at these two equations over here. I've got y is equal to negative x plus 3, and I've got y is equal to negative x minus 2. All right. What I'm going to suggest you do, I'm still going to make you do some work before the end of the lesson. Sketch those quickly. All right. I want you to sketch them on the same graph, and I want you to plot them neatly and carefully. And once you've plotted them on the same set of axes, I want you to tell me what you notice about those two graphs. Okay, so Looney's waiting for you to let her know. Plot them. I want you to tell me what do you notice about those two graphs over there when you plot them. There's something special about them, okay? All right, get that done quickly, guys. And while you're doing that, I'm going to talk about finding the equation of a straight line graph, okay? It's all very well if they give us the equation and they want us to draw the graph, but it can work the other way around as well, where they give us the graph and then obviously we have to give them the equation. It happens, and they definitely require us to know how to do that. So, where do we start? With any graph. If you are having to find the equation of the function that's been given to you, guys, start with the standard equation. Okay, that's your starting point. So because this is a straight line graph, I'm going to start with the standard function or standard equation of ax plus q. All right? Now, the a we're going to work out is our gradient, and the q we know is our y-intercept. Now we've got to very carefully look at our graph and see, well, what information have they given me over here? So what they have quite clearly told me is that I've got a y-intercept of positive 3. Okay, so I know, or we should know, that that then goes into our q, because that's the y-intercept. So let's substitute that in. So I've got y is equal to ax plus 3. And then they've given us this point, which is kind of sitting in the middle of nowhere, but we know that it's where an x value is 8 and the y value is -1. So we've got this coordinate pair which we can work with. And the nice thing about functions is that if you've got a coordinate pair, or if you've got an x value and you need to know what the y value is, we sub it into the equation, okay? So into my equation, where I've got an x, I'm going to substitute 8. And where I've got a y, I'm going to substitute -1. Okay? And I'm sure we can all quite clearly see that the value we're actually looking to now solve for is your a, which is your gradient. Okay, so we're going to land up with -4 over 8, which is equal to a. That's going to simplify to -1/2. Right, let's double check ourselves. This a is negative, which means my gradient is sliding down the hill. If we check ourselves, yes, that gradient is negative, so we write in that. And the other thing, remember, is that the y-intercept was 3, and if we look at our equation, the y-intercept is 3. So the equation of my graph is y equals -1/2 x plus 3. Okay. Right, so there we go. So you've got to look at the information that's been given to you. You have to start with the standard equation, all right? And you substitute in what you know, and you will get there. It's actually quite easy to do. Has anybody come up with the answer to that previous question?
I think Apiwe has, because he says it's a sliding gradient, which means it's got a negative slope.
Okay, he is right with that, but did he mention anything else?
No.
Okay, this is what I want you to notice, guys. If you've plotted it, all right, and I'm going to run out of time, so I'm not going to do all the plotting, but I'll tell you what you're looking for. Do you notice that the gradient in my first equation, which is negative, so you're absolutely right, it's sliding, and the gradient over here are the same. They've both got an a value, which is -1. Okay? Now, this is what we know. If they've both got the same gradient, then what's going to happen is that when we plot them, let's use a straight line so we don't do it badly. When we plot them, if they've got the same gradient, it means that the lines are going to be parallel. Okay, and that becomes a really important concept to know. So any two straight line graphs that have got the same gradient will always be parallel, in which case they run equidistant to each other. All right, so I'm sure some of you guys got that over there, but if you didn't, carry on with the sum, sketch the two equations, and actually test that. Work that out for yourself. And just to make a note that the same gradients give you parallel lines. Okay. Parallel lines. All right, guys. Okay, unfortunately, we're going to have to leave our hyperbolas to next week, but I'm going to be back next week, Monday, and we're going to go through our hyperbolas with you. The hyperbolas, the good news is they're actually really easy. They're not difficult graphs to plot, so we're going to go through those quickly before we go on to our quadratic and our exponential equations. Big section, guys, lots of work to learn, and if you understand the basics, I'm sure those of you in grade 11 and 12 can verify, if you understand the basics, it's not a difficult section. You just got to practice it. That's the thing. You've really got to spend time working on it. Okay. I think at this stage I'm going to hand over back to Looney and say thank you.
Guys, we do have a few questions on the page. So what I'll do is that after the show, I'll ask Tamlin very quickly to just answer what we can answer. But guys, don't you forget, I'll post the show notes on the page so you guys can access them and you guys can get what you need on our page. So thank you so much for tuning in and for being with us on this Earth Day. Don't you forget, the Future Stars competition is still on, guys, till the end of April. So you need to enter yourselves, enter your friends, everyone you can, guys. Tell them to vote for you so that you stand a chance to win the amazing prizes. Thank you so much for tuning in, guys. And until next week, same time, same place on a Monday, grade 10s, we'll see you then.
we've done that, we're going to teach you a little trick. It's called the vertical line test. And this vertical line test is a little trick we use to help us determine if something is a function or not. Okay? Then we learn about the mapping and functional notation. This is important because it's just a type, it's a way of writing. When we're referring to a function, it's the way we refer to a function in our mathematical language. And then we're going to be having a look at sketching. Okay, this is important, guys. Sketching and determining the equation of a linear function. And once we've had a look at that, we're going to learn to sketch and to determine the equation of a hyperbola or a hyperbolic function. All right, so we've got lots of work to do. Hope you guys have got your pens, calculators, and papers ready. Let's have a look at all of this. Okay, key concepts. Let's talk about a relation, all right? Essentially, a relation, all right, is a rule in which each element of the one set of numbers is related to a number in another to another number in another set of values, okay? And we do it according to a specific rule. All right, let me make more sense of that. We have a whole lot of values, x values, and we have a rule. We're going to call it an algebraic rule, okay? So essentially something like y equals 2x plus 3, okay? That's our rule, all right? Now, if we took a whole lot of x values, which we're going to learn are independent values or variables, and we substitute them into the equation. Okay, I'm sure a whole lot of you, or I'm sure you remember from earlier years, our machine diagram. As we feed our variables into the machine, into our rule, so out comes the other values, which we're going to call our dependent variables, and those are our y values, okay? So the relation, the rule in which that we use pairs, okay, ordered pairs would then be saying, instead of having it in this way, I would have a bracket, and I would show that it's negative 2 and 6, like, negative 6, like so. We can show it in set builder notation, or we can show it on the Cartesian plane, where we actually plot the point of negative 2 and negative 6. Okay, that's a very rough drawing, but that's sort of what it would look like on your graph. Okay, so those are different ways that we would represent your relations. All right. Then we talk about two different concepts which we hear quite often when we're dealing with functions and relations. And just to make sure that you guys understand these, we talk about domain and we talk about range. Now, for those of you who have done functions at school, I'm quite sure you've heard this plenty in class. Domain and range, okay? Basically, domain is all the x values that we span across in our set of numbers. So everything from the lowest x value up to the highest x value, that would represent your domain, all right? The range is everything on your y-axis. So your lowest y values up to your highest y values is then your range. So domain, the x values that your function is covering, the range, the y values that your function is covering, okay? And just to show you how we would represent it if I was looking at it on the Cartesian plane, if I had a graph going from negative 2 to positive 2, that's on my x-axis, that would then show me this over here. So I would say that the domain is x as an element from, okay, take note that I've used square brackets over here and over here, grade 10s, to indicate that I'm including negative 2 as. All right, so a function we've established is a relation in which every x value is only ever related to one y value, all right? Relations are where we've got a whole lot of values for x and we stick it into a formula and we work it out inside that formula, and out comes the value for y, giving us our independent x variables and our dependent y variables together, which make coordinate points, which we actually plot when we're actually sketching our functions. Okay. All right, so we've had a look at most of this. Let's just have a quick look over here. So as an example, if I've got a relation is any rule by means of which an element of the first set is associated with at least one element of the second set, we've got an example over here. So let's take, for example, we've got a set of x values giving us negative 2, negative 1, 0, 1 and 2, okay? And we've got this rule, this little relational rule there, which is telling us that y is equal to 3x. Okay, so the idea here, guys, is that each one of these x values gets substituted into the equation of y is equal to 3x. So let me do the first one with you. If I take the x value of -2 and I substitute that into my x, we land up with a value of -6, that being the y value. Okay, and together this little pair will then will ultimately form a coordinate point. Okay, and a coordinate pair is what we plot on our Cartesian plane. Okay, different ways of representing a relation, just so we are aware of it. We can do it by means of a table, just as I've illustrated to you above. All right. We can show relations in terms of order. This thing is going to determine the type of number that comes out when we feed in a value for x. Okay, so it's like a machine diagram as such. When we talk about a function is a special type of relation. Okay, now basically this is what we've got. A function is where every value for x will only ever be related to one value for y. All right? You will never have a value for x related to two values for y if it is a function. So that's what a function is. It's a special type of relation, and that is where its one x value is only ever connected to one y value. All right. Okay. The notations that we briefly mentioned just now, we've got our mapping notation. Okay, the mapping notation, just for now, you can take note of, looks like this. I'm going to discuss it in a bit more detail in a minute. And your functional notation, if you can take a look, just take a note of it, looks like that. It's this f bracket x, which is equal to your rule, your 2x. Okay, so for now, just take a look at it. We'll deal with it now in more detail. And again, we will deal with this in more detail, but if I've got a linear function, all right, a linear function has a special, unique standard equation, all right? And its standard equation is y equals ax plus q. That's the defining equation of a linear function. And a hyperbola has got has got an equation of y equals a over x plus q. And those two equations, if you have got an equation in the form of ax plus q or a over x plus q, it will either give you a graph that is linear or it's going to give you a graph that is a hyperbola. Okay.
Welcome to all you grade 10 math learners, grade 10s. It is a Monday and it's Maths Monday here on Learn Extra Live. I am Looney and with me is Tamlin. How are you doing, Tamlin?
Very well. How are you?
I'm great, thanks. So
Good.
what are we doing on today's show?
Today we're doing a very important section,
Yes.
one which definitely follows its way through from grade 10 all the way to grade 12
Right.
and its functions. So for those out there who are, even if you're in grade 11 or 12, if you're wanting to just revise the basics again, go back to grade 10 basics, watch.
Okay, so you heard it, guys. Tamlin, I'll send you to your board.
Thank you so much.
Guys, don't you forget to contact us on the show throughout the whole show. I'll be on Facebook. Our Facebook page is facebook.com/learnextra. On Twitter, I am on @learnextra. And don't forget to download all your show notes, your schedules, and the videos at learnextra.co.za/live. It is a Monday. It's maths, so grade 10s. I hope you're ready. Let's take the show away. Tamlin?
Thank you so much. Right, welcome Mindsetters, and I hope you are ready to learn a lot about functions today. Okay, today we're actually specifically looking at two types of functions. We're looking at linear and hyperbolic functions. And we're going to take a really close look at what is a function, how does it work, what do we do with it, and hopefully at the end of it you'll have a really good grasp on what it is that we are doing with functions. Okay, so let's have a quick overview as to what we are going to be doing in our lesson today. The first thing we're going to have a look at, guys, is what is a function and a relation. Okay, we're actually going to just define it for you, talk about what they are, all right? Once